Welcome everybody to our Tissue Engineering and Regenerative Medicine panel. As Anna previously mentioned, we continue to work through questions that ask of technological innovations in medicine. How can we repair our bodies? I'm delighted to introduce you to 4 experts in regenerative medicine. So let's go around and meet our panel. First, we have Dr. Ali Kadam Hossein, CEO and founding director at the Terasaki Institute. Next, we have Dr. Samuel Stoop, professor at Northwestern University and director of the Simpson Query Institute. Dr. Amir Sheikhi is the founding director of the Biosoft Materials Laboratory at Penn State, where he is also assistant professor. And finally, we have Dr. Michael Sefton, professor at the University of Toronto and executive director at Medicine by Design. And so all of you have an amazing pedigree and have a lot of experience in biomaterials and regenerative medicine broadly. And so my first question addresses this field as a whole. You each have broad research agendas in your groups, but can you tell us about one project in this space that is most exciting for you? So I'll start with you, Ali.
Sure, yeah. For me, the one that has me very excited is one that's kind of partially in my lab and partially out in trying to get an FDA approval. It's basically a biomaterial used to block blood vessels or fill defects or induce regeneration in the body. And me and a clinician worked on that a few years back, and we've been kind of nursing that along. And now it's in the partially in a startup that's going through the approval process. So I really like that because it's been a journey that's been a few years coming.
Great, thank you. Let's go to you, Sam.
Well, I guess I have to say that the most exciting project in the space in our lab is connected with neural regeneration. We have developed quite interesting self-assembling materials that can repair ruptured axons, and also they can take patient-derived cells that have become induced pluripotent cells, and then our technology takes them to specific phenotypes like motor neurons, which is very difficult to achieve. So we're very excited by that group of projects, all connected with neural regeneration.
Thank you. All right, let's go to you, Amir.
Sure. We are interested in using microfluidic devices to microengineer biomaterials. We break down bulk platforms, for example, hydrogels that have been around for decades, into smaller scale features that we can handpick, engineer, and then put back together and make a bulk material. This way, we can mimic the native tissues or the extracellular matrix of different types of tissues, easily putting things together, building a material that will accelerate the regeneration of tissue. So that is the project that I'm the most excited about.
Sounds very exciting. And finally, let's go to Michael.
So, the one I would pick is we work on a material containing methacrylic acid. It comes in various forms. You can make it in various forms. And the material's somewhat magical. It causes vessels and nerves to regenerate. We're starting to understand why it's working. But our primary use of it now is we're using it to deliver pancreatic islets under the skin in diabetic animals. And so we're following up on that sort of technology, and now also using it to try to manipulate the immune response. Is probably the fundamental challenge left for us in tissue engineering.
Great. All right, so those are our 4 panelists today, and I would like to frame this panel around a question we've been asking throughout this chapter. How do we regenerate functions to our bodies when they're lost? So I'd like to go around the room, and each of you will contribute what you think are the main building blocks that we need to solve this question or to answer this question. So what are the main building blocks that we need to regenerate function to our bodies? So let's go the opposite direction. Let's start with you, Michael.
Okay, so I will take this a slightly different direction. And so what we need to understand, what we need is more understanding, and a lot more understanding of the degeneration processes that give rise to the need for regeneration. And a key element in that are stem cells, and that's why segue into Medicine by Design is the program I run at the University of Toronto. It is focused on employing stem cells and materials and understanding much better than we currently do what is involved in this process of stem cell differentiation and tissue degeneration.
Great, thank you. Okay, let's go to Amir.
Sure. So I think recruiting the right type of cells is probably one of the most important things that we need to do to accelerate the regeneration of tissues. Now imagine we have a boot camp. It's really like a boot camp. We want the right type of soldiers there to construct the tissue. We need to apply something to the tissue to call them, to bring the right type of soldiers there, which are the cells. Then we need to train them. We need to help them differentiate, for example, to the main, basically, type of cells that should be there and prevent the wrong type of cells there. For example, in myocardial infarction, different types of cells can invade the lesion, but if scar is formed with the wrong type of cells, then the tissue is permanently damaged. At the same time, when we have the right type of cells, we need to give it the right tools to build that area. We need to provide the extracellular matrix or a material that mimics the extracellular matrix, at the same time protect it from the immune system so that it's not identified as a foreign body, so they can feel home, start constructing and regenerating the lesion.
Right, yeah, thank you for your analogy, yeah. So from what I understand, we have the soldiers, which are the cells that populate and eventually differentiate based on the signals in their general environment. And sort of the environment in which they are growing is the scaffold that sort of emulates the environment, translates the signals, and really just allows cell proliferation so that you can grow new tissue, for example.
Exactly.
Great, okay. So yeah, I think both Michael and Amir have touched on a lot already. Sam, do you have anything you would like to add?
Well, I would like to add, focused on the use of materials rather than stem cells in regeneration. One thing we need to start with, at least in my opinion, is to consider what are the necessary signals. And the selection of the right signal is critical. I mean, it's been very interesting to me that in spite of the complexity in regeneration, there is always a signal or two signals that are dominant, and the key is to search for what those are, and then once you have selected it, to proceed to molecularly design, providing those signals to cells in the local tissue environment. So this is critical, and it's not sufficient, in my opinion, to just focus on, say, mechanical properties of materials, because even though that's important, it is definitely just a very small slice of the whole problem. I also think, looking into the future, it will not be just selecting the right signal or signals, but also paying attention to the dynamics, let's say, the dance of molecules, to use the name of our panel or symposium, because the dynamic behavior is critical in the way we signal cells externally with materials for regeneration. And this is something that is not very well understood yet. In addition to that, you have the idea of how to control the signals in a temporal sense. When is it time to stop one signal and replace it by another in situ? And this will require, of course, a lot of intelligence in the materials we use.
Great, yeah, I think those are some very good points that I would definitely like to return to later when we discuss some the material side of regenerative medicine. But before then, Ali, do you have anything you would like to add?
So I agree with everything that's been said. I just think that it's very clear that it's a multi-component problem and multifaceted approach. So we discussed a little bit of understanding the biology and understanding how to control the environment to manipulate the biology. So just a couple things that I wanted to add is that I think engineers, tissue engineers, what we try to do is control, take that knowledge of biology and try to control the environment so that the cells, whether they're exogenous cells that we put in, or innate cells in the body, do the right behavior and be able to kind of induce regeneration. So just I think that in the past few years, with the advances in being able to manipulate stem cells or revert stem cells, the genetic clock of cells, as well as use techniques like delivery techniques, the type of stuff that Bob Langer talked about, or CRISPR, or these kinds of tools, I think it's just added a lot more repertoire to our ability to manipulate biology. And I think that's going to help all the approaches, whether it's materials-based, cell and materials-based, or purely cell-based approaches for regeneration.
Yeah, thank you. And I think you touched upon a conundrum that we face in many fields when we start to learn more about a topic and dive really deep is, yes, we are able to develop some amazing tools, but with those extra tools, we dive deep and we get more questions. And so like Michael and Sam touched upon, there's still a lot that we don't know. And so I think that's a testament to the fact that we are progressing very rapidly, but also so rapidly that we have too many questions to count. But I think that says a lot about the space for innovation and discovery for the engineering tools that you talked about, Ali. So that's great. So I'd like to return to Sam's point about identifying the materials that you need. And so Ali, you talked about the exogenous versus endogenous insertion of cells. But I think one of the questions that I had personally was the decision between using synthetic materials versus ones that either are endogenous, comes from fibroblast cells that have been reverted back to iPSCs. So using those factors versus something completely different that you insert into the body and it's purely synthetic. So is there a consensus there of what types of materials we should use and what approaches we should take? So let's start with you, Amir.
Sure, I think each of these approaches come with their pros and cons. If you use a material-based technology, you need to engineer it very well that it mimics the native tissue there, and it can basically accelerate, let's say, cell infiltration, recruiting the right type of cells, changing its properties over time. And by properties, I mean physical and also chemical properties over time, so that it really mimics the environment that cells require to mature and heal the lesion. At the same time, if you go for cell-based therapies, they may be interesting because you are introducing cells that should be there. So you are not dealing with cell recruitment, but at the same time, delivery of the cells can be very challenging. You may lose a lot of cells simply by injecting them, for example. You need to provide an environment for the cells that protects them through injection. At the same time, it enables the cells to receive what they need to behave or to perform as expected. So I would say I do not think there is a consensus there. There are different approaches that are being tried in the field, each of which are can be promising in a certain way, but eventually we need a method that can be easily accessible. It can have a high success rate. We should not actually lose cells through injection, or as you inject the material in the body. We should not significantly change the environment. We should make sure that the material goes away over time. We should make sure that the products of the degradation of material are not toxic over time, and many other aspects that we need to consider.
Great. Yeah, thank you. And I guess I'd like to say on behalf of the other panelists that they probably agree with the fact that there is no consensus between either using synthetic or purely biological and organic materials. But I'd like to dive a little bit deeper in terms of the types of techniques that you are using as it relates to that previous question. So Michael, can you explain about a little bit more about some of the materials and the approach that you're taking? I guess one thing that I'm really interested in learning more about is the methacrylic acid for basically spontaneous angiogenesis. I think that was something that I really wanted to learn more about.
Sure, happy to talk about it. I want to just back up to a previous comment. So when you talk about cells, we don't think about those as organic materials. So those cells are living beings that can do lots of things and can do different things over their lifespan and can become more. So that's a different world than synthetic materials. And it's a key element that I expect we'll get to it eventually is that convergence of these different worlds and how the materials informs the biology informs the materials, how we bring those all together. So you kind of ask the question in an artificial distinction,
okay,
which I wanted to back up on.
Okay, thank you for
material. It's a very simple material. It's just an acid group. It's we use it in different forms. The most recent version is bound to collagen, which we use for wound healing and cell delivery. The simplest version is an injectable gel with polyethylene glycol, kind of standard material, and we use it as a coating on other medical devices. We get vessels, we get nerves. The short answer is, it works somewhat magically. We don't really understand why we get the vessels. We discovered it by serendipity, maybe 20 years ago in the lab when we started seeing vessels when we were using this material. We now know it's an insulin growth factor mediated phenomena. So it's eliciting a particular inflammatory response. And so the key with using materials for any purpose is to understand the inflammatory response, the host response, and learning how to control that foreign body response. We got lucky with methacrylic acid, and the point is now to try to design materials like Sam does, so that one can generate the response you want, knowing just from the dance of the molecules. I like that metaphor.
Great. Yeah, and I think that brings us over to Sam, whose work I first discovered through the dance of molecules. So the peptide sequence that was able to self-assemble itself into the nanorods that you used for the reparation of damaged axons. Right. So what was the creative process behind discovering that peptide sequence?
Well, the process or the approach is self-assembly, right? So it's the notion of programming molecules to create supramolecular structures, which of course have thousands or millions of molecules connected together without chemical bonds, without covalent bonds. And so that process of self-assembly or supramolecular self-assembly we have found it to be extremely versatile and valuable in designing systems for regeneration. We've demonstrated this in bone, in cartilage, and muscle, in dental tissues, in blood vessels, and in neural regeneration, right? So the basic approach is designing molecules that, as I said a few minutes ago, that bear the right signals and have the right architectures. In our case, we use self-assembly to emulate the architecture of the filaments that are present in all mammalian extracellular matrices. And so that was a part of the architectural biomimetics. And in those systems, we embedded the right signals. Now, because in self-assembly, you connect molecules non-covalently, that allows them the freedom to move, which is what I think, their ability to dance, let's say, because that is key in being able to talk to receptors in the cell membrane. The cell is not a flat surface, rigid surface. It's a highly dynamic object engaged in Brownian motion and many other types of motions. And you are coming from the outside to talk to that structure. So you have to be equally dynamic in order to do it effectively. And by not freezing molecules into static structures, but allowing them to adapt to receptors, I think is extremely important. And in my opinion, will be one of the secrets to effective regeneration.
Great. Yeah, I think the dynamic nature of the supramolecular molecules, like you said, perfectly emulates, or maybe not perfectly, but definitely has many of the characteristics that we see in nature, which is truly the original nanotechnology, building things from the bottom up.
That's right. I mean, filaments outside cells, they assemble and disassemble. The best example actually is the intracellular cytoskeleton, right? Of where proteins bond non-covalently to each other in a reversible, reversibly, and therefore provide the function that's needed.
Great. All right, so I'll pass it off to Ali. I would like you to talk a little bit more about what decisions you make behind what materials you choose to use in the biomaterials and regenerative medicine research you have.
Yeah, so I think that's an excellent question. I think in most cases, people, what's good to use for each indication may be somewhat different, because as we've been talking about, biology in the different tissues is different, and what it takes to create the right environment is different. So for us, it's a combination of trying to understand some of the right biology, and then build the materials or in a way that can at least sustain that biology, or kind of modulate it in a particular way. And then the other thing is, for us, we care a lot about processing the materials, and also being able to control the architecture of the materials, which is one of the reasons why we think function does really relate to form. So being able to control the architecture is important. So being able to process these materials is also important. So it's a combination of a few different factors that we use.
Great. Thank you. All right, so to finish off the panel, I'd like to zoom out a little bit. So you have all clearly found great success in the field of regenerative medicine and biomaterials. So I think we're all interested in where it all started. What steps did you take to lead you to where you are today? So let's start with you, Sam.
Okay, what steps did I follow? I mean, that's a really interesting question, right? So I think the steps, or let's say the great fortune I had was to be early on, to be exposed to a very diverse experience in science. And this turned out to be critical for my biomaterials interest, for my interest currently in regenerative medicine. So, this started very early on. I was raised in Costa Rica, a country that's highly focused on education. And there I was exposed to a very wonderful palette of science when I was in my early education. And then at UCLA, where Ali is now, That's my alma mater. I had the fortune of discovering material science there as a chemistry student. So that combined the two things together. My first interest in biomaterials actually occurred at UCLA. And then I came to Northwestern, which is the university that invented the field of material science. And it was here that then I ended up in the dental school and the medical school teaching biomaterials after my PhD was completed. And so this definitely created this very broad exposure, but always maintaining my specialty, which was chemistry, way back. And so, this was, all critical, of course, in being able to somehow begin a journey in regenerative medicine that really forced me to bring all fields into scientific convergence, because you needed chemistry, you needed material science, you needed physics, biology, and all had to be in on common ground because the problem is so complex and challenging, right? So I think this early experiences that I had is what brought me to where I ended up, and in a very beneficial way.
Great, thank you. And yeah, I'm sure that's the same position that many people watching are in right now, getting exposure to many different fields, finding out what they like, and maybe one day putting them all together and making something great out of it. So thank you. All right, Amira, I think I'll turn it to you.
Sure. My journey started with the fundamental, basically, studies during my PhD. I did optical tweezers, lasers for manipulating soft materials. So I started the field with soft materials without even thinking about applications. I did a lot of fundamental studies, but soon I realized that I'm more interested in using the science that I learned to solve real life problems. So I moved to chemistry department. I did my PhD in chemical engineering. I moved to chemistry department. I did 2 years of postdoc there, learned a lot about chemistry. Like Sam said, it's a wonderful world. My experience in science was totally different than my experience in engineering. And then the combination of them encouraged me to go dive even deeper into applications. So I joined Ali's lab and I learned that the sky is the limit. So I started learning about a lot of interesting systems, and soon I started developing my own systems. And yeah, here I am. So it's a combination of a lot of things.
Great. All right, and Michael, we'll go to you.
So, my starting point was I was an undergrad in chemical engineering. I started to hear about things. A professor suggested a kind of area called medical applications of chemistry. Diligence in my third year, and realized that one could do applied chemistry in medicine. The University of Toronto recruited a new faculty member, Paul Lang, who was interested in medical adhesives. And so I did an undergraduate thesis in his lab, and then started working on immobilizing heparin to material as an anticoagulant. I did that as an undergrad, and then went to grad school to work with Ed Merrill, who was sort of my academic father and was Bob Langer's academic grandfather. And so kind of started a large, kind of really one of the first chemical engineers doing materials in medicine. And he kind of began life as a rheologist even. And so I took a PhD. My lab mate was Dick Pepis, across the hallway with Bob Langer. So we were grad students together, and then I was lucky enough to get a job in Toronto as a professor. And I was going to work on diffusion in polymers, was what I had sort of been doing in my PhD bit, because I assumed there were no jobs for chemical engineers doing medical things. My department chair at the time said, no, why? We didn't hire you to do this diffusion and polymer stuff. That's boring. Why don't you work on the medical things that you're doing? So I said, okay, but what happens if the students, where are they going to get a job? And the department chair said, don't worry about it. They'll figure it out. And so I started doing more and more medical things, and then that took over my lab. And I'm 45 years later, I am where I am.
Right. All right. And let's finish it with Ali.
Yeah, no, this is very interesting hearing everyone's stories. In many ways, you see very common themes. I also did chemical engineering at the University of Toronto, where I initially met Professor Sefton and learned and got fascinated.
And he won't call me Michael.
Yeah, Professor Sefton forever. So Professor Sefton basically introduced me to applications of chemical engineering to medicine, and it really blew my socks off. I thought it was really incredible. So when it came time, I did my master's also at University of Toronto, working with Professor Sefton and Peter Zandstrom, more biological stem cell related work. Subsequent to that, I went to MIT because I had heard about this guy, Bob Langer, many times from Professor Sefton, about he's doing some really interesting stuff. So that's where I went, and it again, I got second time, blew my socks off, because I realized that the amount of impact that one person can make, and how much we intrinsically limit ourselves about what the possibilities are. So I think for me, after that was just a combination of being super excited about what I'm doing and just having the long-term vision of continuing and persevering through the difficulties. So I think it was, a combination of great mentors, very inspiring environments at very important times in my life, and then just the passion to continue go forward. So it's been a wonderful journey.
Great. Thank you all for sharing your stories. Those were very, very interesting. And I think one common theme we can draw out is the fact that no one path is ever linear. You kind of just go from one point to the next. And if that's something that aligns with your interests, or you discover something completely new that you never knew before, then maybe that might take you down a completely different path. Let's say starting from chemical engineering and then end up going into biomedical devices and biomaterials. So yeah, thank you very much for sharing your stories. And so I think that finishes our panel, our health panel, this chapter. So thank you very much for your insights into regenerative medicine and giving a glimpse of some of your ongoing work. So thank you, Amir, Michael, Ali, and Sam. Thank you for your time.
Thank you very much.
Okay.
Yeah,
Bye.
thank you. Thanks for having us.
Bye-bye.
Of course.
Bye, everybody.